In this fourth week of the course, we'll discuss strength of evidence. So far, all we considered was how to set up a properly designed study. In Econometrics 1, and we discussed selection issues, so selection was absolutely central, and we discussed how we can deal with non-random selection into treatment, and you should have one of those fabulous 5 research designs. And then in Econometrics 2, we discussed how you can also show whether the treatment effect is larger or smaller for a specific subgroup, whether it varies over time, the treatment effect may actually grow or become smaller. And last week we discussed the mechanisms that could be behind your treatment and the outcome. But now we are going to discuss how much we can actually learn from one empirical study. And so far we implicitly used a very simple decision rule. If you conduct an empirical study, say you write your master thesis and it's empirical work, then if the p-value related to the estimated treatment effect is 0.05 or lower, then we find evidence for an effect of the treatment. And if you don't find a p-value of lower than 0.05, then there's no evidence. And that's all there is to it. And that was so far sort of the our approach, right? So if you do find a p-value of 0.05 or lower, then you say, well, this treatment has an effect, full stop. And all that you learned so far is that the proper way of phrasing this, namely that if your p-value is not lower than 0.05, that you do not say, I do not find an effect of, but you say, I do not find evidence for an effect of. And why is it very important to make this distinction? Because I want to reiterate this point, is that the p-value does not say whether the null hypothesis of no effect is true or not. The p-value is actually calculated under the assumption of no effect. Given all of the issues that come with empirical research, like your data, which may suffer from measurement error, your model, which may not be completely correct, the functional form that you impose on the relationship between the outcome and the treatment, right? So it may well be that you don't find evidence, so that it may well be that you are not able to reject the null hypothesis of no effect because your p-value is actually, for example, 0.10, but that doesn't necessarily mean that there is no effect. And there's this famous saying by Carl Sagan, an astrophysicist, saying, absence of evidence is not evidence of absence. And for him, actually, this was very important because he was actually interested. He did research into extraterrestrial life. Well, so far we have lots of absence of evidence because, well, that we have not found any evidence yet. But he kept on doing his work. He has died by now, but he spent decades and decades looking for evidence of extraterrestrial life, and he kept doing so because not finding evidence of extraterrestrial life on Mars or on a Mars mission does not necessarily mean that there is no life on Mars, and we are still trying to find out. And now by means of the latest Mars mission by this Perseverance, I think is the name of this latest Mars lander. Alright, well, and this lesson that we actually already learned in Econometrics 1 is extremely important, and it goes wrong all the time. There's a nice graph here from an article by Amrein et al. That was published in Nature, showing that in about half of all cases, the authors of a study that do not find evidence of an effect say that there is no effect. So I hope you remember this by the time you write up the conclusions of your master thesis, that if your p-value is higher than 0.05, you do not find evidence of an effect. Alright, but now back to what can we actually learn from the findings of a study. Say now that your estimated effect is really surprising. So, for example, you get a negative sign rather than a positive sign. You're like, what the hell is going on, right? Could it be a sign error here? Or is this really what is going on? Secondly, you find a surprisingly large effect. Maybe there's an error in terms of magnitude, right? Or you find a p-value of 0.70 and you're like, how can this be? I thought I had a pretty accurate design of the study, and still I do not find an effect. That maybe this is a false negative, right? So this all means to question the effects, the results of your study. And obviously, a surprise is only possible if you had some prior. Right? So you had some idea of what to expect about the sign, the size, and also whether you are going to find any effect or no. And if you actually follow a different decision rule, then you can actually integrate that prior, and that's a so-called Bayesian approach. And the idea is as follows: you start actually with a prior, some belief about, for instance, the chance of finding an effect, and then you adjust your prior based on the results of your study. Right, so then in the Bayesian approach, it's more about learning. For instance, it's easily illustrated by an example of the work of a detective. Say that we find a corpse in the house, with some blood, a knife, and all that, and we have 3 suspects here. Now, and the detective first assigns a uniform probability distribution, so says like, well, the chance of any of those 3 individuals being the murderer is 1/3. But then the detective goes to work, finds new information, and adjusts the probabilities. And this guy in the middle here is exonerated. He cannot be the one. So the probability for him goes to 0, and the probability remaining for the other 2 suspects is 1/2. And then the detective digs up further dirt and new information, and then also, and this new information also exonerates this 3rd person here. So, i.e., it must be that this lady here committed this offense. Right? So that's how the Bayesian approach works. You adjust the probabilities rather than with the simple decision rule in the beginning, like we do 1 test and then we know for certain whether it works or no. So we have more. It's not so black and white anymore. It's sort of shades of gray, right? So you keep adjusting your probabilities. And actually, it says 1 here, but this is just an example. But in the Bayesian approach, the probabilities may actually only approach 1, given the evidence. And Nate Silver, a statistician who wrote a very popular book on statistics, The Signal and the Noise, put it this way: we learn about the universe through approximation, getting closer and closer to the truth as we gather more evidence. And so the evidence is the new information, and then we keep reassigning probabilities. And so, for example, we wake up in the world today, we see the sun going up, and then we see it coming up tomorrow again, and we assign a higher and higher probability to the chance of the sun going up tomorrow as well. And it's very different actually from saying, well, what do I know? I just see the sun going up. Nothing is certain. No. The whole idea is that there can be many certain things. There can be all kinds of natural laws, but we are just dumb observers, and we are trying to learn about sort of the truth that is out there. We do that based on observations, new information, new evidence, and then we adjust the chances of an event occurring. And this is a different way of looking at probabilities than we are used to, because so far we addressed what-if questions, and those are called forward causal questions. This is the business of estimation of effects of causes. What happens if I pull this handle? What happens if I increase cooling? How does that affect later earnings? Whereas in the Bayesian approach is more reverse causal inference. We see something happening, so we see the corpse, we see the blood, we see the knife and all that. And then we ask, like, okay, who has done this? There's three suspects, and now we're going to learn who did it. And so that's more a why question. Why did this happen? What are and then you go like, well, what are the possible causes of this effect? Well, we have three of them, and now let's see how we can learn what the most likely cause is of the effect that we observe. You're familiar with the first one, and now we're going to learn about the second one in this week. There's a nice quote here by Gelman and Imbens, who wrote a paper together on the topic why questions motivate what-if questions that can be studied using standard statistical tools such as experiments, observational studies, and structural equation models. I also strongly encourage you to start with why questions in your own research, also with your master thesis, and just look out of your window and be curious and think like, how did this come about? How can it be? Why do we always do things this way? And then if you then go through this questioning and probable causes, then you may come up with a research design to actually test the effect of a certain treatment, a certain policy, certain factor on this outcome. Now, you may recall from an earlier statistics class, or from a statistics class actually, this not being a statistics class, how the updating actually works. This is the actual formula. Let me briefly go over this, but obviously I'll cover this in more detail later on in this knowledge clip. So we have, the two basic elements are your prior, that is the chance of A being true, and your posterior, the chance of A being true given the new evidence. So the chance that John actually killed this guy, but now we find actually some blood of the victim on John. So given that we find blood on John of the victim, how can we adjust our prior? So this is the posterior, prior, posterior. Now, how are we going to learn? With those two elements. So this element here is also called the likelihood. So how accurate a signal is finding blood on a suspect's person, and we actually divide that by the evidence, the probability of B being true. But I'll give you some examples actually, so that you can actually understand this formula. And I'll do so with a classic example from statistics class, namely a medical test. Say that your physician sends you to the hospital to have a test for having cancer or no. And now you go to the hospital, and then actually the test comes out positive. What is then the probability that you actually have cancer, right? If you can still think straight after getting this surprising result. And again, this goes back to the earlier slide, that we don't just take the results of a test or results of an empirical study, but we look at, okay, what do we learn here? How surprising is this? How much more certain can I now be that I actually have cancer or no? Now, what goes into this process of updating is your prior, your posterior, and the accuracy of the test. So, as it says here, the test is not perfect, but it does give a signal. Now, for many types of cancers, it holds that they're pretty rare, right? So let's put that probability at 0.5%, so 0.005. Say that the test is fairly accurate, so it gets it right 99% of the time, which looks very good, but as we'll see, that doesn't necessarily mean that a positive test result means that you do have cancer, right? So, getting it right 99% of the time means that the chance of getting a false negative, so the test says, no, you don't, a negative test result, and so you don't have cancer, basically, that's what the test says. Then there's still a 1% chance that you do have cancer after all. Here, actually, we also have a chance of having a false positive of 1%, which means that if you do not have cancer, you have a 1% chance that the test says, yes, but you do have cancer, right? Now, let's now apply Bayes' rule. So what we want to know is the chance of having cancer given the positive test result. Your prior, that's what we start with here, is 0.005. Right? Now, the likelihood of this test, or the accuracy of this test is 0.99. So, okay, we know that. Now, what's the chance of a positive test result? And to show you that, here's a cheat sheet actually to figure that out. Here, I actually put it all in, I put it in terms of a population of 10,000 people. If there's 10,000 people, then given the prevalence of this type of cancer, 50 of those actually do have this type of cancer, and 9,950 don't. We also know that the chance of a false negative, if you do have cancer, so you are one of those 50, there's still 0.99 times 50, which is approximately 1. So for 1 out of those 50 persons, they get a negative test result. So they go to the hospital, they do have cancer, they don't know this, but they're going to learn about it. But then the test says, no, you don't have cancer. So this is 1, but for 49 out of those 50, actually, we get an accurate signal, right? Similarly, obviously there's a large group that does not have cancer, but given the accuracy of 0.99 and the likelihood of 0.99, almost 100 out of this group gets a positive test result. Right? So, and the way to think about it is that if you have a huge group of people who do not have the disease, then even with a highly accurate test, for example of 99%, still quite a few, 1% of those, 1% of many is still a large number, right? So 99 out of those 9,950 get a positive test result, and the rest gets a negative test result. Now, what's the chance of getting a positive test result? That's 49 plus 99 is 148, divided by 10,000, which is 0.015. Right, so 1.5% of the people in total get a positive test result. That's what we need to know in the denominator. Actually below here I have the same table, but now I put them in terms of probability. Some students find it easier to think in terms of probabilities directly. So if you are one of those, then this is the table to go for. But it's basically the same information. So okay, so we know 0.05, the chance of getting a positive test result. So we divide 0.99 times 0.005 by this 0.015, and the result is our posterior 0.33. So the chance that you do have a cancer given this positive test result is only 33%. The whole point here is that you don't set this posterior to 1 given this test result. And similarly, that's sort of the theme of today, is that if you conduct your an empirical test for your master thesis and you find the statistical effect of a treatment on an outcome, you should also not set the chance that this treatment works to 1, right? It's just one test and it's not a perfectly accurate test. So this is how it works, guys. Alright, so actually to go over this one more time, I actually have a test here. It's a test for anemia actually that I just bought, so I can do this myself. It's actually not for anemia directly, it's actually a test for a deficiency, iron deficiency. And I actually now, to fill out this table, I actually have to stop the screen, so you'll have to look at this. Let me make it a little larger actually. Alright, so now let's see how it works, right? So the chance of having anemia, which is actually pretty common, let's say that it's 0.3. Also given that, I bought this test for a reason. I have a high chance of having anemia in the winter time. So this is obviously much larger than the 0.005 in the cancer case. So this is going to be 0.7 then here. Now we have an accuracy of 0.95, so 0.95. That's the likelihood, right? So the false negatives are then 5%, and also false positives are also 5%. Then let's see, the chance of a positive test result given that I do have anemia is 0.95 times 0.3, right? So and that is equal to, and I computed that already, 0.285. close to 0.3, but not quite. So I still do have some false negatives. Yeah, those are false negatives, and those are equal to 0.015. Now here we go. Then if we do not have anemia, then the chance of getting a positive test result after all is 0.05 times 0.7. So that's 0.05 being equal to 1 minus 0.95. And that is equal to 0.035. So the chance of getting it right, i.e. a negative test result, if I do not have anemia, is 0.665. All right, so then we can just add up those rows. This gets to 0.32. This gets up to 0.68. So what we can now do, I did indeed, the test result was actually positive. So let's see, let's now compute, well, it's not about cancer here, actually it's about anemia. And then, well, let's start with our prior f of 0.3. Well, that's 0.3. The likelihood of the test, so the accuracy of the test, as it says here at the front, is 0.095, which looks very good, but we have learned now that it better be very accurate, because otherwise you get many wrong results. And we divide that by the chance of getting a positive test result, which is 0.32, right? 0.32. So then now I actually know that I have a good chance of having an iron deficiency giving this test result, right? So that's how it works, and you can use it for all kinds of purposes, including one of those self-tests of having the disease or no. Alright, so we've gone through this classic example showing you how the Bayesian process of updating of beliefs actually works. And that's also the perspective you should have on your own empirical work. And so your MSc thesis and the results of your thesis are going to be a noisy signal based on which you are going to update your prior. And the uncertainty is not only the result of this difference between your alternative hypothesis and your null hypothesis of no effect, but it's also related to measurement error in your data. Maybe you got the wrong model. You impose a certain functional form, most likely, a linear relationship, which may actually not be true. You use a specific estimation method and all that. So there's many uncertainties involved. So the accuracy of the statistical test that you're going to conduct in your master thesis is not going to be 100%, but much lower than that. So you should not simply adjust the likelihood of a treatment, that a treatment works, to 1 if you find a statistically significant effect of the treatment in your thesis. There's actually a one-to-one link with the example, and so medical tests are also an empirical test, right? And you should see your own empirical work through the same lens, and it's just like if you look on your smartphone and you get this circle around this sort of point estimate, that it gives you the approximate equation. So it gives you some idea of where we are. It gives you some idea of whether you have cancer, anemia, or some idea of whether this treatment works, but it's not like we have 100% certainty. And there's a nice quote here from Amrein et al. This article that I discussed earlier, published in Nature. All statistics, including p-values and confidence intervals, naturally vary from study to study, and often do so to a surprising degree. In fact, random variation alone can easily lead to large disparities in p-values, far beyond falling just to either side of the 0.05 threshold. For example, even if researchers could conduct 2 perfect replication studies of some genuine effect, each with 80% power, a chance of achieving a p-value of lower than 0.05, it would not be very surprising for one researcher to obtain a p-value of smaller than 0.01 and the other researcher finding a p-value of 0.30. So you should not attach too much value to the findings of your study, even if it's pretty accurate, and that's what this 80% power relates to, and which will something that we will discuss in the next clip. To illustrate this noise in empirical work, here is a graph taken from an article by Bergquist et al. And they look at the effect of social norm treatments on pro-environmental behavior. So we're trying to nudge people in all kinds of ways as a behavioral intervention. And they actually found 91 studies in this area, and see, that the findings are all over the place, right? So if you actually plot those findings, I actually did that for you, then you see that there's quite some variation among those studies. And it may well be that if you add your own study, so you have some kind of nudge that supposedly affects pro-environmental behavior, it may well be that you end up here. Right? So you find a large effect. It's surprisingly large, actually. But it's perfectly possible. There's a good chance of finding such an effect, but it doesn't necessarily mean that we now should totally adjust our posterior towards this value of like 1.2, right? Because you could have also found an effect on the other side of the curve, or sort of here around the median. So Bayes' theorem is all about thinking in terms of gray areas, rather than simply black and white, whether a treatment works or no. We can only say with some probability whether a treatment works, and we keep updating that probability. And so we should really avoid this so-called dichotomania, and just to we should avoid from now on to think in terms of black and white. So what did we learn so far? We should abandon the practice of using a single study as conclusive evidence. And we should see it as a noisy signal, not perfectly accurate, on the basis of which we are going to update our beliefs about the effect of a treatment. And later on, in a later clip, I will show you how this process of Bayesian updating can actually be applied to your own empirical work. The reading of this week is a great article by Ioannidis with the title "Why Most Published Research Findings Are False." And the nice thing is that once you have followed this week of the course, then this article, you can understand this article from beginning to end. And it's an article that has been cited a zillion times, had a major impact, and isn't it nice that you are now able to understand the point that Ioannidis made. The structure of the later clips is as follows. And so we made point one, that a study provides a noisy signal, and we should not follow this dichotomania, thinking in black and white, 0, 1. Secondly, we will apply this way of thinking to the results of your own empirical work, and then we'll see that it all depends on the statistical power of your study, i.e. that if you find a statistically significant effect but the power of your study is very low, then you should not assign too much value to this signal. The third point that I will make is that doing another study clarifies the signal. So doing more than one study can really help, obviously, to learn more about the effect of a treatment. And then finally, you should be careful in interpreting findings from earlier studies because they may well be biased. So that the signal from empirical work may not only be noisy, as I discussed, but it may also be biased.